Yes, let me first thank Joseph and the other organizers for bringing together this really nice meeting in this wonderful place, and also for giving me the opportunity to present some of our work today. And just having seen the other talks of this session on the gauge fields, I still remember, I think it was 17 years ago, I saw Maciek given a talk. I was a young PhD student, and I think on realizing lattice gauge theories, and I think at least part of the audience thought this was completely crazy. So it's interesting or nice to see how these things develop. Okay, I will talk about a slightly different topic. So I will talk about driven and dissipative quantum gas systems, quantum gases of neutral atoms or of photons. And what I'm going to consider is a system, a cloud of particles, atoms or photons, in a structured environment, which will be some lattice potential. And these are driven time periodically in order to engineer some interesting properties and also coupled to some environment, which could, for instance, be a thermal bath. And let me start with a maximally general introduction or motivation for that. Namely, if you have thermal equilibrium, of course, we have this very powerful concept of statistical mechanics, which allows us to compute expectation values. Might still be difficult, but this allows us to really explore the properties of a system theoretically. And these properties of a system depend essentially only on a very few parameters of the environment, which are thermodynamic variables like temperature or chemical potential. Now, if you drive the system out of equilibrium, you don't have such a general concept. And this is often a challenge. However, this is also a great opportunity because it allows you to control states and system properties beyond these very strict constraints of thermal equilibrium by just tuning the way you drive your system or by engineering the environment that you couple your system to. And let me start recapitulating the physics of periodically driven systems without an environment. So we have a Hamiltonian, which is periodic in time. For such a situation, we have generalized steady states of a system, which are called Floquet states, and these consist of a time-periodic Floquet mode and a phase factor with a linearly increasing phase, which is characterized by the quasi-energy. And we can now construct a time-independent effective Hamiltonian, which describes the time evolution in stroboscopic steps of the driving period. So in this way, it looks like a very convenient tool to control the properties of the system by engineering interesting effective Floquet Hamiltonians, as they are called. However, one has to be careful. It's not quite that simple. So if you think about it, this quasi-energy is not defined uniquely, but if you add an integer multiple of h bar omega and you redefine the Floquet mode, this is also a legitimate quasi-energy. And what does that mean? That means essentially that if you consider an unperturbed system which is non-driven, and you have two energy levels which are apart by an integer multiple of h bar omega, when you switch on a perturbation, a time-periodic perturbation, these states appear to be degenerate. I mean, this is resonant coupling as we all know it. And now if you're in a many-body system, such resonances are really ubiquitous. And that means if you have a many-body system, these Floquet modes will be superpositions of states of very different energies. And that means this Floquet Hamiltonian actually describes heating. So it is actually an object which is quite different from a usual static many-body Hamiltonian. And the situation is not that bad. If you drive your system in a way that is favorable, you might achieve a situation, for instance, in large frequencies. You might achieve a situation that this heating just happens very slowly on some heating time, and before you can describe your system by some effective Hamiltonian, which is just a regular Hamiltonian in the sense that it's local, does not describe heating, and hopefully describes some interesting physics. And this is what is known as Floquet engineering. So you have this pre-thermal timescale on which you can influence the properties of your system. And this is just two prominent examples what you can do with it. Namely, you can engineer, for instance, very strong magnetic fields, which for neutral atoms in optical lattices, or also in photonic systems like in optical waveguide systems. And you can engineer magnetic fields, which if you would sort of look at the same thing on graphene, this would correspond to 10,000 Teslas, which are really impossible to achieve in a real lab just using by real magnetic fields. Or you can also realize other models. And these are models which describe so-called topologically non-trivial band structures, which are, without going into the details here, are Bloch bands which have certain topological properties, non-local properties, which are characterized by these Chern numbers, for instance. And if you put them, if you create an edge in your system, then you will have chiral edge modes, which are robust since they transport particles only in one direction. This is just one example what has been achieved. And now the question is, why do you want to sort of consider also coupling such systems to environments? And there's different reasons. So the first reason is that of course, this heating in some experiments might be a problem. So you can engineer situations where it happens rather late, but you cannot always avoid it. And of course, coupling the system to an environment gives you the hope to stabilize states which will not heat up because the dissipation will take out energy of the system. The second motivation is that even if this heating is not an issue, for instance, if you want to prepare, just as an example, a topological insulator state, you have to fill this lowest band completely while keeping the other band empty. And engineering such a situation just by adiabatic loading can be also quite different, because you go to, if you prepare the state, you go through a topological phase transition where bands touch, and this is also non-trivial. So it might be helpful just to prepare such a situation. And finally, you might also construct states which are non-equilibrium steady states, which have nothing in common with the eigenstates of this effective Hamiltonian, but just emerge from the interplay of the driving and the dissipation. And I will give you also an example of that at the end of the talk. And so let us have a look how we describe theoretically such an open Floquet system, open-driven system. So you have your system which is coupled to an environment by a system-Barth coupling, and then you can do a variant of Born-Markov theory to derive a master equation for the limit of weak system-Barth coupling. And this has the following form. As usually, you have a part which is described by the describes the coherent evolution described by the Hamiltonian, and then you have this dissipator. And if you go to the weak coupling limit, when gamma becomes smaller than the energy scales of the system, then you can argue that the steady state will be diagonal in the Floquet states. So why is that? Namely, if the first term here is dominant, this eigenstate, this steady state should be a steady state of the first term. And this can only be the case if it has this diagonal form with respect to the Floquet states. The dissipation is nevertheless important because, first of all, it guides you to this state, because you might need to change energy, for instance, entropy, if you start from a pure state. And also it dictates the populations of these Floquet states in this steady state. And these are obtained by such a classical rate equation where you have rates describing quantum jumps from one Floquet state to another, R and M. And solving this equation gives you this steady state in this limit of very weak system-Barth coupling. And now these rates are obtained also from golden rule type calculations, and they take this type of form. So you have an index mu, which describes the number of driving quanta which are involved in the process of the system-Barth coupling. So the term RMNMu, which describes a transition from N to M, corresponds to a process where the Barth energy changes by minus the quasi-energy change, plus some integer multiple of h bar omega. And this integer could be positive or negative, and essentially that means you can do the very same transition in your system by either going up or down in energy in your Barth. That is the directionality. What means sort of going down in energy or going up in energy in your system is completely meaningless generally. And this is what drives you out of equilibrium, makes the state a non-equilibrium steady state. Namely, the forward and the backward rate do not obey this simple relation as you would have it in equilibrium if these were just non-driven energy eigenstates. And we can also just briefly recapitulate this situation. So if you have an equilibrium system, a non-driven system coupled to a Barth, you have this relation here. And as a result, your steady state is the Gibbs state. And you can plug it into this equation, and as a consequence of this relation here, you find that it solves this sum term by term. So every individual term of this sum vanishes, and these terms describe the probability current between two different eigenstates. And these probability currents thus vanish, and this is what we call detailed balance. Now, in the driven system, This is not the case anymore, since this relation is broken, and now the sum can only vanish as a whole, and as a result, these probabilities depend on very details of the environment and of the driving. And this is what also makes this interesting, because now you can control your state by controlling the environment. And of course, detailed balance is, in this situation, not given anymore, but you have net probability currents in your steady state. And now, this is the situation you find. So with time, the system relaxes to this non-equilibrium steady state, and the question is, can you use this for robust state engineering? And let me give you a first example, which is a simple a scenario where we want to just fill one of these bands of such a topological band structure. And this is work by Alex Schnell, who is a postdoc with me in my group. And so now I showed you the first scenario where the system is described by this effective Hamiltonian, and then it heats up eventually, and the second one where it relaxes to a non-equilibrium steady state. And now the target is, or the question, can we make this non-equilibrium steady state just look like a Gibbs state of this effective Hamiltonian? And we will consider the following concrete examples. So you have a hexagonal lattice which you drive in a way that tunneling is strong always along one direction, and you change this in a circular fashion with time in a periodic fashion, and then you get such a non-trivial topological band structure as I showed it to you, and we now want to fill one of these bands by coupling it to the environment. Okay. Now, this is the rate equation, or the rates that I showed you before already. And as you see, this is broken. We have to sort of restore this relation in order to achieve such a situation. And now, in order to capture these processes where the system exchanges driving quanta h bar omega, one can note that this situation is very similar to a quantum system coupled to a coherent photonic mode in a coherent state. So there is a formalism which describes these problems in what is called the Floquet state, and Floquet space, and this resembles very much the dressed atom picture. So we can think about many copies of our effective Hamiltonian which are shifted by integer multiples of h bar omega, and transitions which sort of emit or absorb driving quanta h bar omega corresponding to single or multiple photon transitions in this picture correspond to transitions between different copies of our system here. And now we see that the multiple or single photon transitions correspond to energy changes in the bath, which are larger than this energy gap here, and transitions within the band correspond to small energies. So if we can engineer a narrow band, we might avoid these unwanted transitions, then get essentially only one of these terms, which obeys now this relation, and then we would get approximately a Gibbs state. And this has been discussed already previously in several papers. Now the question is, how can we do it for a quantum gas experiment? And in particular for this one. And the idea which Alex came up with is that you need, in order to get a narrow bandwidth, you should have a very small mass of the bath particles. And this you can achieve along the direction of the lattice. So this is the hexagon lattice. I think it's a bit hard to see. By just switching off tunneling for the bath particles completely. So we immerse this fermionic two-dimensional system in a weakly interacting Bose gas with no tunneling along the lattice direction, but we have dispersion perpendicular to the lattice. In this way, we have essentially still from the volume a three-dimensional bath, which is much larger than the system, but we can achieve a rather narrow peaked spectral function of this bath. And this width is dictated essentially by the momentum width of your Wannier states of your system particles. And with this, you can achieve rather nicely, if you couple to a bath of low temperature, you can also achieve effectively low temperature states for your effective Hamiltonian. This is with respect to driving amplitude and driving frequency, and there's a vast regime where you have really low temperatures effectively, which are much better if you compare it just to a generic ohmic bath. And if you look at a quantized Hall response in a 12 by 12 unit cell lattice, you see you get nicely results which are very close. So this BC bath is this bath to the situation where you would have a state at zero temperature in your system. So there is some small deviation, which is just a finite size effect here. Okay. This was the first example. The second example is, can you do it also with photons in superconducting circuits, where you might not have a thermal bath, but you can do reservoir engineering. And let's have a system which is described by a Bose-Hubbard model, which describes excitations in artificial atoms. Particles can hop and they interact attractively. And it has been shown, and I will go into the details in a second, that if you couple this system to pumped, leaky cavities, you can cool it if you do it appropriately to its ground state. On the other hand, if you drive your system periodically in time, you can achieve a situation where you create magnetic fluxes in this system, which are described by this effective Hamiltonian. Now the question is, can you do both together? And and the answer will be yes, you can do it, but the result do not look just as if you had the effective Hamiltonian coupled to these cavities, but of course the result is a bit more complicated, but you can still do it. Let me explain. So this is the idea for undriven systems. So you have your spectrum of your system, you couple it virtually to a cavity mode, which is far detuned, so there's only virtual particle exchange. And then you pump this cavity in a red detuned fashion. And so in order to create an excitation in this cavity, you have to borrow energy from your system. And then this excitation can leak out of the system, and this way you can go down in energy and cool your system. Now, if you have the driven system, what happens then? Again, you have all these different copies of your system, and you need a large energy scale h bar omega so that these copies do not overlap, so that there is no resonant excitation. You still need a large sort of detuning from this mode. However, at the same time, these should also not couple directly. So this mode should be detuned from all of these copies. And it gets a bit complicated, essentially also if you have several cavities, which you might need. But at the end, it still works. You need to take into account all these copies, and you can still cool the system. And this is an example for just this 8-side lattice, where you use 3 cavities to essentially prepare the ground state. This is a single particle subspace. You can also do it for a 2-particle subspace. Here we were able to solve just a system with 6 lattice sites, taken into account. These calculations are taking into account also, you need to take into account also copies with different particle numbers, because these fluctuations matter in the physics. So this is why we couldn't do larger systems here, but it also works pretty well still. And of course, it would be nice to extend this a little bit further so that we might get a minimal instance of a fractional quantum Hall state, which is shown to be the ground state of such lattice systems at half flux with repulsive or with hardcore interactions, which you can effectively mimic here by sort of putting the states with 2 particles on one lattice side just off resonant. Okay, so let me now come to a final example where we actually not to try to mimic equilibrium physics, but really use the non-equilibrium nature of such systems. And this is also the main contributor here is Alexander Schnell, and this is a collaboration also with Arthur Videra from Kaiserslautern. And here we now consider again an optical lattice of bosonic atoms. We use parameters for potassium 39, and they can tunnel in this lattice, and we assume them to be non-interacting. And now we couple this to a 3D system, which is another BEC of rubidium atoms. And we use a microscopic description of this using Bogol-Lyubov theory and then Born-Markov theory and so on to describe this. And this bath has a rather high temperature of 2.4 tunneling matrix elements. And now, if you look at the time evolution of this, starting from some high temperature state, you look at the occupations of the single particle eigenstates, and there is not much happening. I mean, you get some occupations which at the end will become thermal, corresponding to that temperature. Now, if you start driving your system locally on one lattice side strongly, and you drive it resonantly, so the driving frequency is 1.5 tunneling matrix elements, so it's 3/8 of the bandwidth. So you really heat up the system. So you couple your single particle eigenstate strongly by the drive. Then you see the following. You see if you compute the population of your Floquet states, you see that one Floquet state really acquires a large occupation. So you get a non-equilibrium Bose condensate just in one of these Floquet states. And this is counterintuitive in a way, because driving the system should actually heat it up further. And the question is there an intuitive explanation? And there is one. Namely, if you look at the eigenmodes of your system, which are given by these sine waves for a box potential, for another potential you would have different ones, which wouldn't be a problem, then you have some modes which completely decouple from the drive because they have a node at the driving side. And if you now look at the eigenstates of the undriven system and look at their maximum overlap with the Floquet states of the driven system, you can really see these modes are not touched by the drive. So the Floquet states so these modes remain to be Floquet states of our system. And now if we look at the energy fluctuations of our Floquet states, we see that all of them have large energy fluctuations, except for those states, of course, which correspond to single particle eigenstates. So these states, in a way, correspond to something like quantum scars. I mean, the term of quantum scars refers to, or quantum many-body scars, refers to systems which are actually generic in the sense that they are ergodic. So in a many-body system is ergodic. It fulfills the eigenstate thermalization hypothesis. That means all states essentially show thermal expectation values, each eigenstate of the system. In a Floquet system, this would mean they would correspond to an infinite temperature ensemble, and they would be superpositions of all energies. This would be in a many-body system. Here we have single particle eigenstates, so these Floquet states do not correspond to superpositions of all energies, but they are still spread out very much in energy. And now scar states are states which are non-ergodic, which are just a few states which are sort of immersed in the spectrum, which happen to be non-ergodic. And if you look at the dynamics of a system and you have a large overlap with such a scar state, the dynamics will be non-ergodic. And here we have these Floquet scar modes or scar-like modes, and they essentially explain the phenomena that we saw. So now we have the driven modes and the undriven scar-like modes. The driven modes are the majority. They are broad in energy. And the scar-like modes are the minority. They have sharp energies, and they have a large level spacing. So now what does the coupling to the environment do? On the one hand, since of the large level spacing, they drive the particles down among the undriven modes. They distribute them approximately equally among the driven modes because all of them are very broad in energy. I mean, this is just a rough hand-waving argument. And then they transport particles from here to here because the mean energies of these modes are typically higher than the mean energy of this low energy mode. And this is what causes this non-equilibrium condensation. And if you wish, this is like a thermoelectric type effect because you have two parts of your system, one which is heated, one which is not heated, and so particles move over from here to here. And this then induces this Bose condensate in an excited mode. Essentially, these blue bullets show the occupation of the K1 mode. And now, this non-equilibrium condensation is something we looked at already earlier. So one can also compare it to equilibrium condensation by looking at how the occupation numbers of single particle orbits change when we increase the density or particle number in our system. Namely, for conventional BC, we see at a certain point when we ramp up the particle number, all occupations saturate, and only the ground state acquires large occupation. And this is essentially when the chemical potential reaches from below the energy of the single particle ground state. And then it can go up, it can't go up further, which explains the saturation, but it can sort of get closer and closer to the lowest state, which explains the BEC in this situation. And now what happens in a driven system, we can see just a picture of an example where we drive a tight binding chain on one end, and on the other hand, it's coupled to a thermal bath. And we see now it's multiple states in this example, which acquire large occupation, and we again have saturation. And you can show analytically, and this is actually not a complicated calculation, but I will not show it to you, that this behavior is generic, and that it's always an odd number of states up here unless you fine-tune your system, maybe to a transition where these states change. And in the previous example I showed you, it was just a single state, this scar-like state, but generally it is always an odd number of states. And let me finally, as a last slide, explain how we calculated these results. So first of all, a good basis of states are Floquet-Fock states. So these are the eigenstates of the driven system if interactions are absent. So these are the occupation number states of the Floquet modes. And then you have a master equation in second quantization, where the only thing you have to know is the quantum jumps describe transitions between individual Floquet modes. And this now happens to be an interacting problem because it's quartic in these jump operators. And why is that? And the reason is that the coupling to the environment is actually a cubic term. You have two field operators for the system making the transition, and the third one destroying or creating a phonon in the bath. And fortunately, in the weak coupling limit, the dynamics decouples the diagonal from the off-diagonal element, so you're left with a classical rate equation, which describes the populations of all these Fock states. So this is still exponentially many probabilities you have to take care of. So this is still difficult to solve directly, but you can very efficiently solve it using Monte Carlo methods, quantum trajectory-like approach, where you generate random walks between the different Fock states and not their superpositions. Or you can write down kinetic equations of motion, where you write down the equation of motion for the mean occupation. Then you have here on the right-hand side two particle correlators, which again tell you that you have an interacting problem. However, you can make a mean field approximation, and both of these, the Monte Carlo simulations, which are quasi-exact on that level of the equation, and these give very accurate results. So this is the kinetic theory, which I showed you before, and these are the Monte Carlo results. And with this, I come to my conclusion or summary, and let me thank again all the people that were involved in this work, and yeah, I think I should stop now.
Thank you very much for your talk. The floor is open for questions. We've got one right here in the gray.
Yeah, thank you for this talk. I have a question about the third example you talk about, the Floquet-induced BEC. I was wondering, you choose the thermal bath to be BEC condensate itself. Is there any special reason that you need the thermal reservoir itself to be a BEC? And I'm also curious, after your BEC is formed inside this optical lattice, what happened to this thermal reservoir?
So first of all, we need a BEC because, I mean, there's other reservoirs you might think of. This is just, I would say, a natural choice in a quantum gas experiment. It needs to be interacting, so in order to thermalize sort of itself. This is why it's a we describe it using Bogoliubov theory. And of course, you could also use a Fermi gas, but it wouldn't thermalize as well. But this was just an easy choice, and I think it works. And the BEC is, of course, assumed to be much larger than the system. So this is a 1D system immersed in a 3D BEC. And that allows you the BEC to absorb a lot of energy before really changing its temperature and eventually changing its properties. So this is, so in that sense, we have a transient evolution because the BEC will eventually sort of heat up. But the reasoning is that this will happen much slower than this non-equilibrium steady state is reached.
Thank you.
All right, so we'll go to this one in the back.
Hi there. And the last experiment you were mentioning with the with Artur Videra,
yes,
where you have this driven these non-interacting particles in this driven lattice, and you get these scar states.
Yes.
Is there a connection to dynamical localization? Because when you flash on a lattice, you get a realization of the kicked rotor.
Yes.
Where you get effects like dynamical localization. So I was wondering if these, which is a sort of integrable style behavior, you get non-chaotic,
yes,
it destroys the classical chaos, as it were. Are these scar states related to that?
No, actually not. But so what they are essentially, so you're right in the sense that by driving the system, you create sort of a chaotic scenario where, however, before you drive the system, it's regular. And you just keep some of these regular states by not touching them by driving. This is what we do here. So we just, if you would use sort of, and in this, here in this box potential, they are just sine waves with a certain wave number, which happen to have a node here. If you had a different potential, it would be difficult to create many scar states, but if you wanted to address a single target state, you could still do it by just putting sort of the drive on a site where this wave function you're addressing has a node, then you would have a single one. And as long as it is low enough in energy, you could also do the same thing. And what is interesting, or what I find interesting about this approach, is that you could also think about generalizing it to many-body systems. So if you would, for instance, have a many-body system and you manage not to drive the ground state, or not to drive a specific state, you could also hope to engineer a way to efficiently cool the system to this particular state, which is non-driven. So this is pretty generic, I think.
Okay, let's do one question here, and then the last one we'll do here.
Yes, over there. Okay, I think I have not understood. Do you populate the green state over there, or you do not populate the green states when you drive on this site?
So we populate essentially one of these green states. So first of all, these green states they remain non-driven. So let me just show you this again. So the red states are very broad in energy. So the bath just redistributes particles among them almost evenly. I mean, not perfectly. These undriven states, they have a very large level spacing, which is why we have a very efficient transport via the bath to the lowest energy state of these states, which is not the ground state of the undriven system, but an excited state. And then, since these states have all mean energies which are higher than this state, you also have this transport from here to here. So you populate one of these scar-like states.
Okay. And so then on your other figure with the occupation number, is there anything interesting to look at is there any temperature actually for the underlying states that are not populated? Like, do you have an effective temperature on those things? I guess no, because otherwise you would not be able to have multiple state populated.
So we didn't check that, but what we have a state with the same temperature, but more particles on these, and higher chemical potential essentially just on these modes here. So this is enough because first of all, the first excited state in this manifold is further separated from this state because the level splitting is large. And second, we have a higher chemical potential because we have this transport of particles from here to here. So the temperature is the same, but you have, let's say, fewer states, or you have a higher density and a larger level splitting, which makes this condensation. If you just look at these states, and here this is a completely non-equilibrium distribution, but this is just hand waving, and we didn't check it, but this is, I think, an intuitive picture.
Okay, thank you.
Yeah, I was just wondering whether you expect this similar behavior if you switch on the interactions between the potassium-39 atoms, so that there really is one mode growing. So what do you think happens when there are interactions between the atoms?
Yes, so if you switch on interaction between the atoms, of course, you get, so what you can do, I mean, I don't know what happens if you switch on strong interaction. It's a difficult problem, but what you can do is you can treat similar things on a mean field level by taking into account interactions at least on a Gross-Pitayevsky or Bogoliubov type approach, which is also not so easy because the rates to the bath depend on the state, so it's a self-consistent, you can do a time evolution where at every point in time you diagonalize your mean field Hamiltonian, get your rates, and integrate a little bit further. And then it looks like a little bit of interactions don't hurt. If you get stronger interactions, you get different types of effects, which are also interesting but different.
Okay, thanks.
Okay, well, with that, I'll let everybody get to their coffee. Thanks to André and to all of our speakers from this morning for some great talks.